All right, now that you know something about what parametric equations are, we're going to talk about some of the basic calculus behind parametric equations and try to connect it to calculus that we know already. We've got a parametric equation here. We've got x equals t squared, y equals t cubed minus 3t. First thing I'm going to talk about is just simply how to find the derivative of something in a dy dx when you've got parametric equations. And the simple way to do that, you could try to solve, like eliminate the parameters and things like we saw in the first section, but you don't have to do any of that. A quick way to find dy dx is simply to find dy dt and divide that by dx dt. You can almost think of this algebraically as the dt's canceling out on each other, but you can just simply take the derivative of your y parameter, so 3t squared minus 3, and take the derivative of your x parameter. And that's going to be the derivative of this parametric, almost like system of equations here, where it's still in terms of t. And you can use that derivative just like you would use any other derivative. Like if you want to find the equation of the tangent line, well, first you would need the slope of the tangent line. You would need the slope of this tangent line when t equals 2 here. Just sub in 2 here, so that's going to be 9 on top over 6 on the bottom. So this is going to be the slope of your tangent line. So it's going to be y minus something equals my slope. I guess I could have reduced that. X minus something. That t equals 2 doesn't go in either of these places. We're looking for an x coordinate and a y coordinate when t equals 2. So you're going to have to plug in the 2 for t back up here. X is 2 squared. Y is 8 minus 6 is 2. So that's not t equals 2, that's y equals 2 that I got from plugging in there. And this would be the equation of my tangent line. So same things you would do with regular x and y equations, just dy dt over dx dt will give you your dy dx. I think that's the key thing to remember there. Is a lot of times you'll have to use that first derivative and not want to do a bunch of algebra to try to get this back in terms of x and y. All right, so that's the first derivative. If you need the second derivative of one of these things, unfortunately it's a little bit more obnoxious. You can't just do the second derivative of y. You can't do like the derivative of dy dt over the derivative of dx dt. It just doesn't work that way, unfortunately. To get the second derivative of something that's parametric, you take the derivative of dy dx with respect to time. So that thing we got on the last slide, we're going to use that again. I brought that over so we could have it here. And that's going to be over just dx dt. The same dx dt that we've already done. X was t squared, so dx dt was 2t. So here, if I want the second derivative of this thing, if I'm looking for, that's how we write the second derivative, I start by taking the derivative of dy dx with respect to t. So that's going to require me to do some quotient rule, or do some algebra. Let's just do some quotient rule. The derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. That's the top of this derivative, and that's going to go over just dx dt. Just that. That's an expression for the second derivative. I don't think you're going to find a time they're going to have to simplify this. Almost every time you get a parametric equation problem, you'll have your calculator. And I think I gave you the calculator on every problem from the book in these sections. The AP problems we'll look at in the next couple of videos are all calculator problems, so I don't think you have to get too far into that. But so that's how you find the second derivative of a parametric equation. Derivative of dy dx, but then it's over dx dt again. Right? So that's your second derivative. Less likely you're going to use a second derivative than the first derivative, but I want you to see it for sure. What you will normally see with parametric equations is more motion problems. I talked at the beginning of the first video how this really is just kind of our third time through motion. So quick review of something we know about motion. If you want to find total distance traveled in a problem, we integrate to do that. We integrate from whatever to whatever. And we integrate for total distance, we integrate absolute value of the velocity. Right? That's something you know. Or if you just integrate velocity, you get displacement. And how far are you from your starting point? As opposed to total distance traveled, where it might be a longer total distance traveled because your particle might be changing directions. Right? That's the formula that we've used to find total distance in the past. And remember that the absolute value of velocity is speed. This here is speed. So if you integrate speed, you get total distance traveled. If you integrate velocity, you get displacement. Right? Velocity and speed are very similar, but speed does not have a sign associated with it. There's not a positive or a negative speed. Like on your speedometer in your car, you're always going a positive speed. If you take the absolute value of the velocity, that gives you the speed. So keeping that in mind, I want to talk about how we can find total distance traveled with a parametric situation. If you've got an x in terms of t and you've got a y in terms of t. Well, first I want to talk about how to get the speed of something in terms of parametric equations. To find speed, you're going to take the square root of dx dt squared plus dy dt squared. That's how you get the speed for a particle using parametric things. And we'll see that tomorrow when you look at some, well, hopefully tomorrow, because it snows some more. But the next time we watch a video, you'll see this in terms of an AP problem. That's how you find the speed of a particle in motion, taking the derivatives of both parameters and then do it. Basically, it's a Pythagorean theorem type thing. If you kind of see an a squared plus b squared thing, and that's not an accident. And it's kind of, if you think about moving in the x direction and moving in the y direction, if you just want a speed combining those two things, this is your dx dt and this is your dy dt, then you would get that third side of your triangle by doing a Pythagorean theorem. This squared plus this squared equals this. This right here is your speed. Now, if you've done anything in physics with vectors, you're pretty bored with me telling you this right now. But that's where that comes from. Don't feel like you have to memorize that or anything, or know where it comes from, but you should know how to find the speed of a particle just by taking the derivative of both and doing a Pythagorean theorem thing with it. Since this is the expression for speed, and notice we don't have to worry about absolute value bars here because everything turns out positive in this expression. If I want the total distance with parametric equations, the same total distance, I can integrate the speed. Just like I did with back in the day when we just had moving along the x-axis or something. Since this is the speed, if I integrate this speed, that'll give me my total distance traveled from wherever to wherever. So it's the same concept as it was before, but now everything's in terms of t. Integrate your speed. This is speed. Integrate your speed, you're going to get total distance traveled. Math 9, calculator will do all of that for us again, or maybe the problem just says set this up but do not evaluate. Sometimes you'll see something like that if it's a nastier expression. So that's total distance with parametric equations. That's total distance with old-time single variable equations. I wanted to show you this first for two reasons. One, before I show you this last slide. Total distance, speed and distance are things that you see a lot on the AP problems. We'll see that in the next couple of videos. But this expression is an important expression by itself, just sort of in generic calculus that gets applied to motion things. But I'm not sure if you know what this is yet, because I don't know what day you're watching this. We may have talked about something called arc length in class already. So this may be a review to you. If it's not, if it snowed a whole bunch in January and we haven't gotten to chapter 8, which is where arc length is yet, this is the expression for arc length. If it's not familiar to you right now, don't worry about it too much. Just recognize that you can get an arc length by integrating some kind of expression here. For parametric equations, you get that arc length by doing, this is the exact same thing as total distance traveled that we just saw on the last board. Integrate the speed, square root of dx dt squared plus dy dt squared. That's the arc length. Because arc length, if you don't know what arc length is, or even if you do, and this would be like a little review for you, the arc length of something is simply how long a path is. And if I've got something that's not linear, and I want to say how long is this thing? Well, you would figure out how long that is by like stretching it out so that it becomes linear, and then measuring that linear distance, like pulling on the ends of this, so we just have a linear distance. So that's the length of that arc. That's also the distance that something is traveling. If you've got a particle, hang on, I have a particle. If you have a particle, and the particle's moving in more than one direction, not in a straight line, and you want to know what's the total distance that particle traveled, that's the same idea as arc length. So by stretching this straight and finding a total distance traveled, you can use the exact same expression we saw on the last slide for total distance traveled. So I just wanted to show you that total distance and arc length are the same thing, which may be something you know already, or maybe not. Over the next couple of videos, we'll look at some AP free response problems with our calculator. Do the problems in the book. Now, there are more than the first video, sorry about that, but since there are several different calculus ideas here, I wanted to make sure you saw them all. Remember, all the answers are there in the packet for you, so if you get stuck on one, just look through what the Book of Knowledge says about it. Use your calculator to speed things up. Be careful out there if you're sledding, don't turn into Ethan Frome. I'll see you next time.